This podcast is brought to you by LMU Munich.
Well, a couple of years ago, David Merman said something rather ominous. He said, "Quantum mechanics is the most useful and powerful theory physicists have ever devised. Yet today, nearly 90 years after its formulation, disagreement about the meaning of the theory is stronger than ever. New interpretations appear every year, none ever disappear." So of a man who would write this, what do you think he would do? Well, within a year or so after that, he decided that finally, after all these years, he would choose an interpretation of quantum mechanics for himself. At the time, we were calling it quantum Bayesianism. I guess by that time I had started calling it QBism. But if you would like to read more about QBism, then I'd say write down some of these references, or you can look them up easily enough. For the philosopher, and I'm guessing everyone in the audience is a philosopher, there are no physicists here? Good. If you were a physicist, I'd say read something that Merman had written. So if you see the name Merman, that means he wrote it. So Fuchs, Merman, and Schoch, Merman wrote it. But for the philosophers in the audience, I'd say the most comprehensive philosophical statement is in this one paper of mine that I've never had the nerve to submit to a philosophy journal. And maybe I never will. But it is the most comprehensive philosophical statement. QBism. Here's this problem. We've have the year after year debate in quantum foundations about the interpretation of the formalism, the interpretation of the theory, and here we come along and propose yet something else that might be called an interpretation. All of these things are symptoms of a problem, I think, and I would like to say that part of the mandate of this newer interpretation is to solve the problem. And what do I see as what the problem is? Why is it that we have a year after year debate on the interpretation of quantum mechanics? About the time I first started thinking about these things, well, actually it was precipitated by a conversation with Lucian Hardy in some meeting in, I think, Hull, England. It must have been around 1996. Hardy and I were walking around, and I asked him, "How do you know when you've made progress in the foundations of quantum mechanics?" And Hardy, if you knew how he talks, you could just imagine this. He kind of said in a very humble way, "That's a good question. That's a really good question. We never asked that question." Well, that bothered me, and I wondered how would we measure whether we've made progress? And after thinking about it for some time, I finally came up with something that I like. What I have here is a picture of quantum mechanics as it's usually taught in a textbook. So you're introduced to the ideas of quantum mechanics, and you're told that there are these things called quantum systems, and associated with the systems, with each system is a complex vector space or Hilbert space, that measurements correspond to Hermitian operators or the bases that diagonalize those Hermitian operators, and that quantum states correspond to density operators on the Hilbert space, and so forth and so on. This is given as a fundamental statement of what the theory is about. But look at this kind of structure that you see in front of you and compare it, I would say, to one of the other great theories of the last century, namely special relativity. When this is taught to a young student, they're very quickly introduced to the idea that there are a couple of crisp physical ideas that lie behind the theory. For instance, that the speed of light is constant. This looks like a tautology. It's not really. Speed of light is constant. And that physics should be the same in all reference frames. And then under the leadership of Einstein, one takes these two very crisp physical statements and massages them into something that looks every bit as mathematical as that. That's the theory of special relativity. But note the distinction. With relativity, you start with that, and you end with something of the structure like that. Whereas with quantum mechanics, we come from the opposite end. So it seems to me that anything that's going to be a good interpretation of quantum mechanics should, in the end, settle this question. It should find some way of posing the theory so that we have it in terms of a couple of crisp physical statements. And that's the foundation of it all. How do we get there? How do we get there? Well, we need to get there, and I've forgotten the slide was here. You just caught me. We need to get there because of this thing that John Wheeler said. If one really understood the central point of quantum theory and its necessity in the construction of the world, one ought to be able to state in one clear, simple sentence. Should be able to state the theory in one clear, simple sentence. Until we see the quantum principle with this simplicity, we can well believe that we do not know the first thing about the universe. John was a rather dramatic man when he was around, but this is essentially what I'm saying. We need to find some way of posing quantum mechanics that we have it in terms of a couple of crisp physical statements. Now I can ask you, how do we get there? Well, this is what we think that this view of things, QBism, is about. And that is that an essential move that needs to be made along the tracks of getting to something like that is to clarify various concepts in the theory. To try to pose the theory in a way that it is logically consistent all the way through. That no philosopher in this group can come up and say, oh, I can point out a flaw in the consistency of your point of view. So that's what we want to aim for first. And one of the things I'm going to show you guys toward the end of the talk is that we can translate some of this clarification that we achieve with this point of view into new questions that should be addressed mathematically, and actually new questions that should be addressed philosophically, that I think you haven't had the opportunity to think about before because the formalism was in a different form than would be needed to ask the kinds of questions that I'll ask at the end. So you'll see what I'm talking about when we get there. So I call the view QBism now. I didn't expect it when I started calling it QBism, but reporters like QBism because they can choose a Picasso painting and put in their articles, and that's helped us quite a bit. QBism, I initially meant to stand for quantum Bayesianism, but whenever I gave this talk, like at our being a Bayesian in a quantum world, I've discovered the thing that I.J. Good said, that there are 46,556, I believe, or 440, some number of Bayesians. There's a large number of Bayesians, lots of varieties of Bayesians. And there were a lot of Bayesians who felt that QBism, quantum Bayesianism, had hijacked the term because it represented a kind of Bayesianism that was not their kind of Bayesianism. So that seemed like a bad thing. For the most part, QBism is aligned with Bruno De Finetti's notion of probability theory. So David Merman suggested that maybe the B is really Bruno, quantum Brunoism. But that doesn't work either. In my quest to find some accurate meaning for it, I lighted on the term, don't laugh, betabilitarianism. Quantum betabilitarianism. Where this word comes from, actually, is a Chief Justice of the United States Supreme Court, Oliver Wendell Holmes Jr., in the early part of the century. Here's something that Louis Menand wrote in his really, really good book called The Metaphysical Club. If anybody wants to learn about American pragmatism because you haven't learned about it in your philosophy courses, because it's been forgotten about in the philosophical world, from what I understand. Read Menand's book, The Metaphysical Club. You'll learn a lot about early American pragmatism. Menand says, the loss of certainty as a phrase is a phrase intellectual historians have used to characterize the period in which Holmes lived. But the phrase has it backward. It was not the loss of certainty that stimulated the 19th century thinkers with whom Holmes associated. It was the discovery of uncertainty. And I have that bold-faced, the discovery of uncertainty. Holmes was, in many respects, a materialist. He believed, as he put it, that the law of the grub is the law for man. He was not a determinist because he did not think that the course of human events was fixed. Complete certainty was an illusion, of that he was certain. There were only greater and lesser degrees of certainty, and that was enough. In fact, it was better than enough. For although we always want to reduce the degree of uncertainty in our lives, we never want it to disappear entirely, or at least I don't. Since uncertainty is what puts the play in the joints. Imprecision, the sportiveness, as it were, of the quantum, is what makes life interesting and change possible. Holmes liked to call himself a betabilitarian. We cannot know what consequences the universe will attach to our choices, but we can bet on them, and we do it every day. So the kind of point of view that Holmes had in his mind was that the world was indeterministic. Really, there's this phrase, there was some play in the joints. The future wasn't uniquely determined by the past. But what he was concerned about, what he was concerned with, was what you need to do to make it in this world. What can you do to help decrease the uncertainty in your own life, in spite of the fact that the world is ultimately indeterministic? I think here's a good way of thinking about everything that I'll tell you in the remainder of the talk, a way to think about QBism. I only dreamed this up 2 talks ago, so it's not very tested, and I'll test it on you guys. Consider this single-celled entity, the euglena. It has this lovely tail that helps it get around in its environment. You can think of the tail as an adaptation to the environment, and the tail as a tool that helps the euglena survive. Over the course of evolution, we've ended up with an entity like this, and it has this lovely instrument that helps it find food and helps it shape its environment to some extent. The tail is not arbitrary. It's brought about in part because of the environment. And in a way, it reflects what kind of environment the entity is in. If the environment had been different through Darwinian evolution, presumably the tail would have been different, or maybe there wouldn't have been a tail at all. So here's the point. The tail is an instrument, much in the same way like in Yossi's talk, we were talking about instruments. It's a tool that this entity has evolved so that it better survives in its environment. Well, the way I want to think of quantum theory, or what I'm aiming for in this thing called QBism, is a way of thinking of quantum theory as a kind of tail that humanity or rational beings developed around 1925. It helps us get around in this environment, better survive in the environment that we're in. If the world had been different, if it hadn't been quantum mechanical, or if it had been something else that's not quantum mechanical, not classical mechanical, we would have developed different strategies for our betting to help us survive in this world. The strategy that we have chosen, or that we have developed, is quantum mechanics. That represents something about the way the world is. So even if I tell you a quantum state is an instrument, or a quantum time evolution operator should be thought of instrumentistically, it doesn't mean that there's no reflection of reality whatsoever in the formalism. This was a nice point that Itamar Potofsky made when he was alive. he would say that any instrumentalism can be viewed as a kind of realism at a higher level. When you ask the question, why these instrumentalities rather than some other instrumentalities? So to the extent that you can analyze that question, you're taking a realist stance and you can do some realist explorations. So the view here is that of QBism, it's an attempt to view quantum theory in something like Darwinian or biologistic terms. This is a term of use around Dewey's philosophy. I don't know if it's more general in philosophy as a whole. It's an attempt to view quantum mechanics in these kinds of terms, but with a larger goal. I'm a physicist. I'm a practicing physicist, not a philosopher. I'd like this to not be the end of the story, but instead the beginning of the next story. And the larger goal that I have in mind is to use this exploration as a means to say something positive about the soup we're swimming in, say something ontologically about the stuff of the world, and to understand our latitude for modifying the world around us to our purposes. In other words, to what extent can we take advantage of this play in the joints? Okay, so now let me start to put together some of the ingredients of QBism for you. Here's something that we take as rather sacrosanct. It's a quote by Martin Gardner. The hypothesis that there is an external world, not dependent on human minds, made of something, is so obviously useful and so strongly confirmed by experience down through the ages that we can say, without exaggerating, that it is better confirmed than any other empirical hypothesis. That's the starting point of QBism. Always keep this in mind. If you have a knee-jerk reaction that says, that guy is a solipsist, or that guy is an instrumentalist, or that guy is an anti-realist, take your mind back to this quote and say, well, why did he show us this quote if he really is so damned anti-realist? Maybe I'm missing something. Okay, so keep that in mind. There's a real world out there, and it's made of bricks. There it is. So there's some stuff out in the world, and actually I have a bad habit of always drawing the stuff out in the world as little cubes. So you'll see a lot of little cubes in this talk. This is your first introduction to them. So there's some stuff out in the world. When we use quantum mechanics to talk about the stuff in the world, we start drawing symbols like this, like these wave functions. The question at hand is, how should we view the relation between the stuff out in the world and these little symbols that the physicists draw? One possibility is that we might think of these symbols as representative of properties of the stuff out in the world. In other words, we might think of the quantum states as attached in some logical sense to the objects themselves, that this quantum state psi is a property of the object. That's one possible stance that could be developed. QBism takes a kind of opposite stance and says that this psi is more representative of us, the agent talking about some quantum object, than the object itself. Asher Perez put it this way: there's a lot of dead people in my talk. And that's sad. This guy was a very good friend of mine when he was still around. A wave function is not something which exists in nature, he was fond of saying, and forthrightly so. Just looking at the structure of this thing, a wave function is not something which exists in nature, kind of takes us back to Yossi's talk when he gave a quote of De Finetti. Here's my modification of it. My thesis, paradoxically and a little provocatively, but nonetheless genuinely, is simply this: quantum states do not exist. The abandonment of superstitious beliefs about the existence of phlogiston, the cosmic ether, absolute space and time, or fairies and witches was an essential step along the road to scientific thinking. The quantum state, too, if regarded as something endowed with some kind of objective existence, is no less a misleading conception an illusory attempt to exteriorize or materialize our actual probabilistic beliefs. And I've used Yossi's translation for this and just slipped it in without the square brackets. So this is the point of view being explored here, that this symbol here should be thought of as something like a subjective Bayesian probability distribution. At the moment I'm saying like. By the end of the talk I'll saying it should be thought of as a subjective Bayesian probability distribution. It should be thought of something like that, and one actually should take everything that De Finetti says about probabilities just as seriously for quantum states. So that's one piece of QBism. Okay, but now a quantum state is not obviously a probability. Where you see obvious probabilities in quantum theory is through an application of the Born rule. So I don't know whether you guys are used to this kind of notation, but I'm in the habit of thinking of quantum states not in terms directly of these state vectors, but rather projection operators onto state vectors. So I think when I say a quantum state, I'm thinking of a projection operator or perhaps a convex combination of projection operators or something called a density operator. And when I'm thinking of density operators, I usually use the symbol rho, which I think was introduced by von Neumann in his 1932 book, and probably before that, for general quantum states, general density operators. So one takes a quantum state, and one takes some kind of representation for measurements, and you calculate probabilities from a combination of quantum state and measurement operators according to something called the Born rule. So now we obviously have probabilities after an application of the Born rule. How should we think of these probabilities? Well, QBism takes the point of view of a Dutch book definition, or something like a Dutch book definition of probabilities. To declare a probability P sub E means that you will buy or sell a lottery ticket that's worth $1 if E for this many dollars, worth €1 if E for P sub E euro cents. And it means nothing more than that. That's the very definition of it all. Where you get the structure of probability theory, like Yossi emphasized, is you get it from the requirement that you never put yourself in a position of inevitably losing money. So this is a normative requirement. So you say to yourself, well, let me consider how I would, what price I would buy and sell these tickets for, $1 if E or F. And let me consider what I would buy and sell these tickets for, $1 if E, worth $1 if F, so forth. And if I want to make sure that I never have a sure loss, I may lose, of course, but if I want to guard against a sure loss, then I had better adjust my prices so that this relation holds. That's the Dutch book definition. So you get some of the structure of probability theory. In fact, you get all of the structure of probability theory from this normative requirement, that this is what you should aim for in the prices that you would pay for tickets. It's like Dennis Lindley said, the Bayesian subjectivist or coherent paradigm is egocentric. It's about how one person, there's only one person on the outside of the gambler's desk here. He's wearing an orange hat, the national color of the Netherlands. The Bayesian subjectivist or coherent paradigm is egocentric. It's a tale of one person contemplating the world and not wishing to be stupid or technically incoherent. He realizes that to do this, his statements of uncertainties must be probabilistic and they should be coherent in the way that we were talking about. Now, I say that this is a normative requirement. Why don't I just make it an absolute requirement? Oh, yeah, I mean, we notice it's a tale of one person contemplating the world, not wishing to be coherent. I mean, not wishing to be incoherent. He doesn't say that you must be coherent, that you must be a rational agent. So I want to stick to the normative notion of probability, and the reason is none of us are ever coherent, and none of us ever will be truly, truly coherent, in the sense that all of our probabilistic ascriptions, that they all fit together according to the rules of probability. And the reason is I can talk about this event or that event, then I should make sure that I'm coherent on this set. But of course, there's always more things that I could consider, and I'd better make sure that I'm coherent with my probability assignments for those as well. In principle, there's an infinite mesh of propositions that I should consider and ask myself how I would gamble on them. Since I can't do that, it becomes a question of time or money, and at some point I just cut it all out and I say, okay, it's time to gamble without further consideration. So coherence is something you aim for. You try to make the mesh as large as you can possibly make it, but you never really achieve full coherence. Now, of this Dutch book argument, one can ask, does it make a commitment to some kind of ontology? Most of the time, one sees Bayesian probabilities characterized as measures of ignorance. In the physics community, particularly, a lot of people have been influenced by a physicist named E.T. Jaynes, Edwin T. Jaynes, and he habitually talked about probabilities as being measures of ignorance. But a point I'd like to make is that that description carries with it a metaphysical commitment that's not necessary for personalist Bayesianism. Just think about the phrase imperfect knowledge. It sounds like something that, at least in one's imagination, could be perfected, making all probabilities 0 or 1. In this case, one uses probabilities only because one does not know the true pre-existing state of affairs. But all that really matters for the subjectivist Bayesian is that there's uncertainty for whatever reason. There might be uncertainty because there's ignorance. I mean, there might be a true state of affairs that you don't know about, and therefore you have some uncertainty. But there might be uncertainty because the world itself doesn't yet know what it'll give. There might be an objective indeterminism, and you wouldn't be too smart to pass up the tools of probability theory, even in a world where there's objective indeterminism, even in a world where God openly walks out and says, you know, David Lewis's principle is really without content. It would still be good to use coherent probabilities. So, go back to the title. We had subjective, I don't know, what was it? What was the title? Something about subjective quantum states, even in a world with objective indeterminism. This is the sort of thing that I'm thinking. Here's an extreme case of the meaning of probability, the case of certainty. What do I mean by a probability one statement? From this point of view, a probability one statement means I will buy or sell a lottery ticket that's worth $1, if E, for in fact $1, full stop. So if you would say of the definition of probability 0.999 that what it means is that I will buy a ticket that's worth $1 for 0.999 cents, then it would seem like a strange thing to change your definition by the time you get to probability 1. So we hold hard and fast on this, that this is all it means. Particularly, probability 1 does not imply the truth of a proposition. It doesn't imply that the truth of a proposition is pre-existent, and I have no idea what I was thinking about when I wrote this last one. Isolated truth. I don't know. But here's a spot where QBism follows Ludwig Wittgenstein on about page 15 of his book on certainty. You find this lovely thing. Certainty is, as it were, a tone of voice in which one declares how things are, but one does not infer from the tone of voice that one is justified. Well, believe it or not, we take this stuff seriously, and we're going to use it to prove something in a little bit. Okay, so that's what the notion of probability in QBism is. Now let's try to settle another thing. When we write down probabilities, probability of something, of H, We're talking about the measurements, at least as I've introduced it so far, we were writing down probabilities for measurement outcomes. Should I think of the measurement outcomes of a quantum measurement as revealing some kind of pre-existing but unknown value for something about the physical system? Or might I think about the measurement outcomes as something that's created in the process of the measurement? What's not the character? So the question here is not what is the character of the P's. That, at least I've given an answer to. You might agree with it, you might not, but we've already given an answer to what is the character of the P's. The question now is what is the character of the H's that the probabilities are written about? Are the H's something that's already out there, or are the H's something that come into existence in the process of measurement? Well, I'm going to express an opinion on it, and it's going to be based on some things that we learned from Einstein, Podolsky, and Rosen. I'm going to invoke the EPR criterion of reality, which I guess all of you have already seen somewhere in your studies. If without in any way disturbing a system, this is my addition, one can gather the information required to predict with certainty, i.e. with probability equal to unity, the value of a physical quantity, then there exists an element of physical reality corresponding to this physical quantity. So you can see already where we might make use of this declaration, because we would say there's really no grounds already to accept the EPR criterion of reality. A probability one assignment doesn't necessarily mean that there's a physical quantity having that. What it means is there's an agent who's willing to throw away all of his money on it. Well, okay, so I have my little problem with that already. But I'm a pretty mild person. You ought to compare this to Wolfgang Pauli, who wrote Heisenberg soon after the paper appeared. He said to Pauli, Einstein has once more made public remarks on quantum mechanics in Physical Review of May 15th, with Podolsky and Rosen, no good company, by the way. As is well known, this always amounts to a catastrophe when it happens. I love this about Wolfgang Pauli. Admittedly, I would like to grant him that, should an undergraduate advance objections of this kind, I would consider him quite intelligent and promising. You might say that Pauli already felt some things in his bones, but we're going to have to tease them out a little bit. Okay, so here's what I want to do. I want to accept this notion of reality that Einstein, Podolsky, and Rosen. Now, I've already told you that a QBist would already start to question it, because we wouldn't want to make the link between probability 1 and existence in the way that they do. But let's just give them...
Sufficient condition, you see, it's not if and only if, but just if. So the criterion does not give a definition. Sorry, reality is just it's sufficient. They don't say if and only if.
That's right. They don't say if and only if. And so now I'm going to go on the attack on the other side, actually. In other words, I would say, well, look, just because we have a probability 1 assignment doesn't mean reality. Let's give them their due. Let's suppose that there is nonetheless, and see where that goes. So here's the way I want to use this. What I'd like to consider is a kind of modern version of EPR, where my two physical systems are not two particles with position and momentum, but instead two little cubes that have three-dimensional Hilbert spaces, Q-trits, people call them in the quantum information community. And let me assume locality in the following sense, that nothing I do here changes anything physical over here. It doesn't change a state of reality over here by doing things over here. It doesn't change it instantaneously anyway. Now, suppose that I measure the left one in any way that I'd like, say, two possible observables, one corresponding to one orthonormal basis, the other one corresponding to a different orthonormal basis. Well, if I were to do this, if I were to, for instance, perform the purple measurement, if you can see that it's purple, then what I would tell myself is whatever outcome I get over here for this basis, like I get this outcome, then if I were to go over to this one and make the same measurement, I make the prediction that with probability 1, I'll find the same outcome. Alternatively, I could consider the green basis that's rotated a bit. I perform the measurement, and I tell myself, well, if I get this outcome on the first one, then I know that if I go to the second one, I'll get exactly the same outcome. I'll make a probability 1 prediction. So what EPR said was there is an element of reality associated with the purple basis, and there's an element of reality associated with the green basis that we might think of these elements of reality as being associated with little wiggling fingers. So if I get this outcome, see my wiggling thumb on the left side, then I can ascribe an element of reality among this triple on the right side corresponding to the wiggling finger, whichever one is wiggling. And similarly, I could do it for the other basis. And that's where they left it. And then Bohr came along, and so they said, look, the quantum formalism is incomplete because quantum mechanics doesn't give us the tools for describing these elements of reality that I've just identified, that we EPR, have just identified for you. That's where they left it. Bohr came along with a reply that people are still trying to figure out what he had said. And I myself most recently reread it again. I have no idea what the guy is saying. But then, so this is the little story that I just told you guys. But then someone very clever, or two very clever people came along. One of them is still alive, the other one's dead. Koshin and Specker. Simon Koshin, he pronounces his name in a kind of American way. I guess you guys wouldn't pronounce it that way. And Ernst Specker, he passed away just a couple of years ago. And they said, let's not just consider 2 possible measurements, let's consider 45 of them. Something along those lines. And they pointed out the following. We could use the same argumentation to say, well, if we had considered this measurement, we could identify an element of reality. If we'd used this measurement, we could identify an element of reality. If we'd used this measurement, we could identify an element of reality, and so forth. They went down the list. But they chose their measurement bases in a very clever way so that they were interlocked in a certain way. So there's this basis, and suppose we get to this outcome. That means we can assume that over there, we'd also get this outcome. And then they considered this basis. See, I'm just rotating around one finger. And then they'd say, oh, well, then it has to be the case that we would get exactly the same outcome for that one. And then so forth. And they interlocked and they rotated and rotated until they found a logical contradiction. They were able to find a basis such that if you suppose that this one is colored green, we can start doing some rotations until we get back, and now it's colored red. And then they said, what does this mean? Well, the conclusion is you hold on to reality, then you have to give up the EPR criterion of reality, the necessary side of whichever of the two it is. Alternatively, you can give up the idea of locality. QBism opts for the latter, for the former. We hold on to the idea of locality, and consequently, we feel that both necessary and sufficient conditions on EPR, if we had attempted it, go by the wayside. So we take this stance. Quantum measurements are generative. Fancy word I made up once and don't like, really. I don't know why I keep using this slide. Their outcomes do not pre-exist before the measurement. That's all I really mean by that. They arise from the very process. So we've taken a stance on probability theory. We've taken a stance on the meaning of the outcomes, that we shouldn't think of these H's as representing states of some kind of pre-existent reality, but rather the consequences of measurement interactions. If we put it all together in a package, it's something that I got in the habit of calling the Paulian idea. And if you know, this book is really not selling very well. So if you want to give a gift to, you know, some young person for Christmas, give them the Notes on the Pallian Idea. Here's the Pallian Idea in 2 parts. And this will cap off what QBism means. Pallian Idea number 2. In quantum mechanics, an observation changes in general the state of the observed system. He puts it in quotes because he's a little worried about what he's saying. Of the observed system in a way not contained in any mathematically formulated laws. As it is allowed to consider the instruments of observation as a kind of prolongation of the sense organs of the observer, I consider the unpredictable change by any single observation to be an abandonment of the idea of the isolation or the detachment of the observer from the course of physical events outside himself. So here's a key point. I'm not going to read this. Here's a key point for this. Pauli said, what are these measuring instruments? And he felt compelled by logic to ultimately say, we should think of the instruments as not, you know, we shouldn't think, like I was telling you today, in a tripartite way. There's the object, there's a measuring instrument, and there is the agent or the observer who's writing down probabilities. Pauli said, well, really the only consistent way to think about this is to think of the measurement instruments as part of the observer or part of the gambling agent himself. That's one piece of the Pallian idea. The other piece of it is this little conversation that Pauli had with Einstein. Einstein said, physics is, after all, the description of reality. He said to me with a sideways glance or something like that. This question clearly shows his concern that the objective character of physics might be lost through a theory of the type of quantum mechanics, in that, as a consequence of its wider conception of objectivity, an explanation of nature, the difference between physical reality and dream or hallucination become blurred. Einstein was worried that the world would disappear in a big dream or illusion. Pauli, though, says, the objectivity of physics is, however, fully ensured in quantum mechanics in the following sense. It's a kind of Dilthian idea, if anybody remembers the philosopher Dilthey. Although in principle, according to the theory, it is in general only the statistics of experiments that is determined by laws, the observer is unable in the unpredictable single case to influence the result of his observation. So he may influence it in the sense of setting measurement devices, but once measuring devices are set, the reality of the world comes back and bites him in the sense of giving him a surprise. So if at any point he's questioning whether there's a world out there that's not just a dream, Pauli would say he sees it with the unpredictable outcome of a measurement. Einstein, however, advocated a narrower form of the reality concept, which assumes a complete separation of an objectively existing physical state from any mode of its observation. One reason I love this quote is because, at least ever since I've known Stefan, people have called me a solipsist, and they say I don't believe in a real world, and things like this. And Pauli kind of says, in your face, not only are we realists, we believe in a bigger form of reality than you guys do. Einstein's notion of reality, he thought, was a narrow conception of reality. So here's the story of QBism in one diagram. The diagram is this. Here's the way we should think of the situation we have in quantum mechanics. There is something called an agent, an active agent, a gambling agent, and there is a quantum system. We break the world into 2 pieces, the agent and the system. Maybe that's a Kantian thing, a subject and an object. But I want to think of them in slightly different terms, agent and object, agent and system. We break the world into 2 pieces. What quantum mechanics is about is this agent taking actions on this system. These things on this guy's hands are meant to represent measuring instruments. This is the left-hand side of the picture is something that I stole from John Wheeler, and he had these little measuring instruments on on their hands. So we should think of measurements as actions that are taken on systems. They have unpredictable consequences. What are the consequences of measurement outcomes? From our point of view, they're the experiences of the agent who's made the action. The reason I put this little quantum state here near the head of the agent is because I want to remind you that this thing, if it is a property of anything at all, it's a property of the agent, the one who's making the gambles. It's the probability assignments he would make. So this is the story of QBism. It's the story of action on the external world and the consequences we receive, and quantum mechanics should be thought of as a formalism that helps us gamble on those things. You've already sensed that I'm bitter about being called a solipsist, because I don't know how many times I've shown this diagram and people have said, so you don't believe in a real world? And I say, what part of this diagram do you not get? There is an observer, but there's also something external to the observer. If I were really a solipsist, I would just draw that. And I didn't. Okay. Not only can we talk about agents with single systems in front of him, we can talk about agents with two systems in front of him. He can take actions on this one, and he can take actions on that one, and he can take actions on any number of systems. What constitutes a system? Do systems have to be atoms and molecules, or can they be whiteboard markers and chairs or professors? Well, from the point of view here, quantum mechanics is a structure for gambling that any agent can use. So quantum mechanics can be used by this guy, or this guy, or this guy, or this guy. But now the question of whether a professor can be an object, or is he something special because he's a user of the theory, it's a question of perspective from QBism's point of view. Here he is, and he's got a physical system on him that he can, in front of him, that he can take actions on. Just like in this photo, there was one in front of him that he could take actions on. But there are also other ones that he could take actions on. And the way to think about further agents, the professors out there in the world, is to think of them also as little cubes. He can take actions on this cube, he can take actions on that cube. What I'm trying to get at is that we see no reason to make any pieces of the world special. I'm an agent, I can gamble on any piece of the world, which includes everybody out here in the audience, and when I do so, I would treat you quantum mechanically. All right, let's go back to this now, in my remaining 10 minutes. What does this lead us to say about the Born rule? Well, if we view the laws of probability in a normative sense, I would say that the big conclusion of this way of thinking is that we should think of the Born rule in a normative sense. We shouldn't think of the Born rule as a law of nature, like the standard laws of nature that one sees, for instance, in Maxwell's theory of the electromagnetic field, where to be an electromagnetic field, you must satisfy a certain set of equations. And if you don't satisfy these equations, you're no electromagnetic field. Probabilities, it's different. No probabilities ultimately are coherent, at least from this point of view. Probabilities are more like the Ten Commandments, things that you shouldn't do this, you shouldn't do that. You shouldn't put yourself in a situation where you'll lose money for sure. But I'd like to make this explicit, this idea that the Born rule is a statement of coherence, and it struck me today that since I'm giving a talk in front of a mathematical center for philosophy, I should pose a little bit of mathematics, give you something to think about, actually. I mean, what else is mathematical philosophy for if it's not to think about some mathematical questions in quantum foundations? To that end, what I want to do is just quickly tell you about a development that I and my students and some other collaborators around the world have been pushing to bring to some kind of completion, and that is to find another formalism for quantum theory. So in philosophical discussions, for the most part, people talk about quantum states and operators on complex vector spaces and so forth. What I'd like to do to change the discussion is find a different formalism, let's say like Feynman's path integral formalism, for discussing quantum mechanics, and seeing if that changes the dialogue of what is the various philosophical issues, of what are the various philosophical issues to do with quantum mechanics. And for this, I want to lean on something that Richard Feynman said in an article called The Concept of Probability in Quantum Mechanics from 1951. And this is really nice. He says, the new theory asserts that there are experiments for which the exact outcome is fundamentally unpredictable, and in these cases, one has to be satisfied with computing probabilities of various outcomes. But far more fundamental was the discovery that in nature, the laws of combining probabilities were not those of the classical probability theory. It's not the concept of probability that changes, and he says what I mean by probability is the usual thing. If you look in his 1964 book, you'll see that what he means by the usual thing is a Bayesian notion of probability. What is changed, and changed radically, is the method of calculating probabilities. Can we see the Born rule, this thing back here, in that kind of light, as a change of how to calculate probabilities? And once we see it in that kind of light, can we give it a kind of normative interpretation? Well, you can. And the technique goes like this. If we can find a way of rewriting the formalism so that it's not about quantum states ever, but always about probability distributions, then we can see the Born rule particularly as an expression of a relation between various probabilities. The way you can do that is to think that outside of Paris, not only is there a Bureau of Standards that has the standard meter stick and the standard kilogram, but for every quantum system I want to invent something that I'll call the standard quantum measurement. The role of the standard quantum measurement is this. If the measurement were informative enough so that if I were to take my quantum system and throw it in the measurement device, and I knew the probabilities for the outcomes, if the probabilities were so informative that they re-specified the quantum state to begin with, then I could have the formalism that I'm looking for. So the sort of situation I'm wanting to consider is that I have a quantum system, I imagine throwing it up into a device in the Bureau of Standards, the probabilities uniquely tell me what the quantum state is, and at the point that I recognize that they uniquely tell me what the quantum state is, I can just start using these probabilities in all my calculations. Then one can talk about other measuring devices, other measurements that one might perform. And one can ask, what would happen if I throw this system into here rather than up there? And what you get is, well, normally you'd use the Born rule, but in this rewriting of it, we would use this probability to calculate these probabilities. If you're really careful, here's where all the mathematics comes from. So tonight, when we have beer, let's come back to the mathematics. If you're really careful and you choose your measuring device right, you can end up with a kind of scenario like this. And I'll conclude the talk very soon. Consider this. I have down here on the ground, I'm going to call this the ground, and that one up there, the sky. On the ground, I've got some kind of von Neumann measurement, any one you want. And by the way, what I mean by a quantum system here is a finite dimensional one that lives on a Hilbert space of size d, dimension d. I'm going to throw my quantum system into this measuring device, and what I would like to know are what probabilities I should use for the outcomes of that measuring device. You say, well, give me the quantum state and give me the measurement operators and I'll calculate it for you. But if you had one of these Bureau of Standards measurements and you choose it just right, then what I can give you instead is the probabilities for the outcomes of the Bureau of Standards measuring device. And I could give you the probability for the outcomes of this thing, given that I got a certain one for the measuring device. So this is what I'm really going to do. I'm really going to throw this into here. But I want to analyze this probability in terms of a prior probability for the imaginary measurement up in the sky and a conditional probability for the ground given the imaginary measurement up in the sky. And I skipped all of the details, but here's what I want to claim. For any von Neumann measurement you can consider down here, and a measurement of just the right style for up here, you can find a relation between all of these probabilities. But it's not the classical Bayesian relation that says the probability for the measurement outcome on the ground is given by the usual formula for the prior probability and the conditional probabilities. It's not that. Quantum mechanics says that's wrong. But quantum mechanics puts something in its place. It says, I'll give you a way of writing the actual measurement in terms of the counterfactual measurement or the hypothetical measurement. And it's this, if you've chosen these things just right. It turns out you can write down a formalism for quantum theory so that you don't use measurements operators, you don't use quantum states, but instead you use probabilities all the way through. And the lovely thing about it is that it turns out to be a nearly trivial change from the classical Bayesian probability law. The change is that you multiply by a factor that has to do with the dimension of the system, and you do a little bit of renormalization at the end so that everything holds. So there it is again. From this point of view, the classical law of total probability is a kind of subroutine for calculating the probabilities. And as a center for mathematical philosophy, I don't know exactly what you would want to say about this, but I think that there's much more of a story that needs to be told. And so far I haven't been able to reconstruct all of it myself. But you can imagine putting the terms of quantum mechanics in a different kind of language of probabilities, and therefore changing the debate to some extent, at least in terms of the natural terms for the debate. I had a little bit more that I wanted to tell you about indeterminism, but my time is up, so I'm just going to go to a picture of William James and leave it at that. Thank you.